Hey, welcome back. Today we're going to be talking about how to solve integration-based impulse problems, specifically for AP Physics C Mechanics students. So we have lately been talking about how the derivative of momentum with respect to time is going to be force. Now we're going to do sort of an opposite style problem where we're going to integrate. There is an equation on your equation sheet that looks like this. And this J, in case you don't know, stands for impulse. I don't actually use that very often as a variable, but it is something to be aware of. It stands for impulse. That is equal to a change in momentum, and that is the integral of force with respect to time. So, fair enough. Let's take a look at the problem that we have here. So it says a 5 kilogram object is propelled from rest at time t equals 0. It should say the sum of the forces always acts in the same direction. The magnitude of the sum of the forces is given as a function of t in seconds by, and then we have the sum of the forces is equal to 0.5 times t. Okay, and so that is our force function. With that, we can take the integral of that with respect to time. Okay, and so we can say the integral of force with respect to time is going to be equal to our change in momentum. Now that's not our final answer, but that's going to get us closer to our final answer. So we can say therefore our change in momentum is equal to the integral of 0.5 t dt. Well, fair enough, that 0.5 can be pulled out in front, so we can say delta p is equal to 0.5 times the integral of t dt. And we have our bounds, let's not forget our bounds. So we go from t equals 0, so let me actually label this slightly better. So I'm going to say t is equal to 0, this will be t equals 4. Okay, so what do we have here? We have delta p is going to be equal to 0.5, and this becomes t squared over 2. And so that is evaluated from t equals 0 to t equals 4. Alright, so let's continue. We say delta p is equal to 0.5 times 4 squared over 2. That's embedded in the problem, so to speak, the squared function, minus 0. And we can kind of forget about that term. So delta p is going to be equal to 0.5 times 16 over 2. Okay, well what is that? Well, that would be delta p is going to be equal to 0.5 times 8. And so our delta p is going to be equal to 4. So that's the change in momentum. And you want to think about, well, what are our units of momentum? So remember, momentum is m times v. These units are going to be kilograms. These units down here are going to be meters per seconds. So we're talking about in units of kilograms times meters per seconds. Okay, so that's the change in momentum. But what is the speed of the object? So what is the speed of the object? So we now know what the change in momentum is. Let's do this. We could say, just to make it clear, that's a delta p actually, right? And so what does that mean? Well, that means therefore that p final minus p initial is equal to 4 kilograms times meters per seconds. Well, we know our p initial is 0, so our p final, well, what does our p final mean? Well, that would be m times v final is equal to 4 kilograms times meters per seconds. Okay, so can you all see where I'm going here? Let's move this over here. We don't have much room. So we want to get our V final. So our V final is going to be 4 kilograms times meters per seconds divided by 5, divided by our mass, right? So our mass with 5 kilograms over here. So our V final is 4/5 or 0.8 meters per seconds. So that's how you go about doing a problem like this. It just has the inverse relationship that we have previously talked about. By the way, if you want more help on the inverse of this, I'll put a link to that lesson in the upper right about now, where you can solve a problem like taking the derivative of a momentum function will give you the force. So that's that. I do want to say though that I've gone over lessons for an entire year of physics as well as almost all of the ideas for an AP Physics C Mechanics class. So if you have any questions or comments down below, please let me know. And I hope you all have a great day. Take care.